Good morning and welcome. My name is Siva Raghupati. I'm a Principal Solutions Architect at Amazon Web Services. Today morning, I have the pleasure of introducing Valentino Bolonghi. Valentino is the CTO at AdRoll, an ad tech company which is doing ad retargeting, and he will talk about that in more detail. I want to tell you a little story before we get started. I had the pleasure of meeting Valentino about 2.5 or 3 years ago, and at that point, we recently launched Amazon DynamoDB, which is our NoSQL store, and I was a member of the team, as well as I was consulting with customers and architecting their systems. He says he wanted to use DynamoDB, so we got it off in this discussion. I was in San Francisco. Then he says, by the way, do you have an Erlang driver for DynamoDB? Erlang, for those of you who don't know what Erlang is, it's a concurrent programming language and for real-time systems. And I was scratching my head and seeing, well, yeah, we really don't have an Erlang driver. We only have a Java driver at this point. Then he said, that's OK. Can you point me to the source? In about a few days, he whips up an Erlang driver for DynamoDB and has this stuff going. And he's one of those rare luminaries that every time I hang out with him, I learn one or two things. So without much ado, I want to have Valentino run with the presentation. I'll be coming towards the end, wrapping up the presentation. We're delighted to be here at 9 a.m. On Friday after an awesome party. So let's get started. So,
yes. Thank you. Hey, everyone. Thanks for being here at the first day of the conference, fresh. And I'm going to do my best to try to live up to all the kind words that Siva just said. I think I'm going to stay over on this side. So yes, I'm Valentino, CTO at AdRoll, and what we do, as Siva said, is ad retargeting. That's a very complex term to say that basically whenever somebody on the web browses your site, and this site is one of our customers, we drop a little cookie. We do one thing called syncing our cookies with all of the big traffic exchanges on the web. And then whenever you browse sites like the New York Times or your favorite blog or your favorite sports site, we can then, using machine learning, determine how much, try to figure out what interests were linked to your browser. And then at that point, we can determine how much to pay and return a request. How often do we do this in a day? We do this 60 billion times. So that's about the traffic that happens on the web. More or less on the publishing side of the web. And this doesn't include the data collection, which is another billion requests per day at least. And effectively, this per se is already a very complicated task. I'm going to say it somewhat often during the talk, but 60 billion requests per day, 1% of that is 600 million. So if your infrastructure has a problem 1% of the time, you're going to generate 600 million errors. And you better not want to log all of those things and be trying to figure out how to avoid even the error entirely. But if this wasn't in itself just a big accomplishment, for comparison, I think WhatsApp was talking about something between 20 and 30 billion messages per day. So with the same language and similar infrastructure as WhatsApp, you can get up to even 16+ billion requests per day. But of course, as I said, 1% is 600 million impressions, and 1% downtime is going to cost us a lot more than $1 million. So on top of this, if we're not collecting data or we're not properly buying advertising for our customers, it's our customers that are paying by not being able to leverage all of our advertising and our products and the positive return that we have on the investment that they do with us. So in all of this, we need to stay up. And again, if this was it, you can try to figure out a way, and you somehow try to figure out a solution, but you need to do it cheaply. Advertising is one of the most competitive areas in software. A lot of people might be scared away by the jargon or by the fact that advertising is annoying and whatnot, but as a matter of fact, there's a lot of competition, and we need to have positive margins like everybody. So it's very important for us that the infrastructure on which we run scales non-linearly with the revenue that the company is generating. We need to be able to onboard customers really, really quickly without needing to spend all of the money that we make every single day. And yeah, all of these are great requirements, and everything is topped up by a really, really simple 100 millisecond max latency that we need to respect. There's a lot of talk about real-time systems and so on. This is an actual real-time system, one of those in the traditional sense. There are three, in literature, there are really three types of real-time systems. There are soft real-time systems, are typically identified by the fact that the results might not land in the deadline time, and they're still going to be useful, and the system is not going to fail, but effectively the performance or the quality of the service is going to degrade over time. There are hard real-time systems, things like the braking system on your cars. And these systems are a little bit different, they're a little bit more complex. You cannot violate the deadline. If you violate the deadline even once, the entire system falls apart and it needs to shut down because it means that it's not going to be able to make decisions properly. And then there are firm real-time systems, which is what Adderall is. In firm real-time systems, the deadline, after the deadline, the result is absolutely useless. A big, big secret for how our machines are capable of handling that amount of impressions every day is that they are capable of understanding how often a request is going to take inside the system. And as soon as it reaches the threshold, the request is completely removed. It's much better for us to not serve an impression or to lose one impression rather than running into a timeout and afterwards crashing the entire systems. If we don't meet this latency often enough, what is going to happen is that all of the exchanges that we work with are going to start to reduce the traffic that they send to us because they think that we are in trouble. Again, 1% of error over 60 billion is a lot of errors, and it's a lot of errors for everyone involved, whether they are Google or Facebook or Yahoo or any other huge exchange on the web. So it's really, really important that the systems remain at that latency constantly throughout the entire day. Even 1% timeout throughout the day is unacceptable. And so there is a big problem with 100 millisecond latency, very big one. The world is a fairly big place, and the speed of light in vacuum is about 300,000 kilometers per second. In fiber, it's about 200,000 kilometers per second. And the web, the internet is just not only fiber. There's a lot of hops, there's a lot of copper. And the distance, if you were to take two random cities like Paris and New York, which everybody should know, I think, the distance between them is about 66,000 kilometers, and the round-trip time of light is about 60 milliseconds. So basically, if we were to do all of our bidding for Europe inside the US, 60% of the time that we have available to return a result would be completely gone just by the connection handshake. So because of this, exchanges do a couple of things. Number one, they only work with persistent keep-alive connections that use pipelining. So a connection, once it's opened by an exchange, is going to stay open for a day. And usually, typically, an exchange opens up a few thousand connections, and it's going to send many thousands of requests in every one of these connections. So your machines and your load balancer and your infrastructure need to be ready to keep a lot of connections alive constantly. And the other thing that you have to do in order to work around the problem of speed of light, besides, of course, designing an infrastructure that is going to reply within a few hundred milliseconds, is to be able to have a global presence. So using AWS, we're capable of reaching all of the places where there are big traffic exchanges in the world, and we're close to the sources of traffic for all of them. Basically, with the system as we have set it up right now, it takes us about a week to open up one of these regions and fill them up with data. We're talking about 30 terabytes of data compressed per day that we need to ship across all of these regions. As a comparison of what 30 terabytes of data means, it's about a petabyte per month, and it's the equivalent in 3 days. Basically, the uncompressed version of this is equivalent to how much data the entire US stock exchange market is going to generate in a year, just in 3 days. So the amount of data that is flowing through the system is pretty ridiculous, and it's a very big requirement that we have in terms of what we're capable to ship around the world, the bandwidth that we need. Just the ability to create a bandwidth from your own data center in Singapore to your own data center in West Coast US or East Coast US, it is a daunting task. We are moving several hundreds of terabytes every week from Singapore to the US, and the bandwidth required with the throughput that we need is going to be extremely expensive for us. At the same time, we need extremely low response time for every one of the databases that we use on the real-time request pipe. As a matter of fact, we need less than 5 milliseconds, which gives us a space of about being able to do 2, and in some cases, 3 requests for every 1 request that we receive. And the volume of requests that we receive is fairly huge. At 60 billion requests per day, on peak time, we receive about 60 million requests per minute. That's about 1 million requests per second. And they are going to query data from 100 billion items that we store, that we need to be able to store in our key value store. And so starting with the database, and then we're going to go up throughout the chain of our infrastructure, we're going to touch the different decisions that we made and the lessons that we learned throughout our last 7 years. So the first thing, we needed to choose a database, and we ended up choosing DynamoDB. I've done multiple talks about DynamoDB over the years, and it really is a fascinating and incredible database. We really don't have to worry much about it, but before we got to choosing DynamoDB, we tried many other solutions. We went with the first solutions were things like Memcache. We really hoped to get Memcache to work. It was very, very simple. The only problem is that Memcache tends to die and lose everything that was stored inside Memcache. When the instance runs out of memory, Memcache removes keys from its memory store. And so that's unfortunately not something that we can do. That's data that we use for bidding. It's directly correlated with dollars. Our machine learning improves its performance the more data we can keep close to the machines. And that's really a big requirement, and it's going to lose many percentage points of revenue if we don't do that. We tried then Redis. It's going to back everything up on disk, and it doesn't expire keys and so on. It's great. It's open source. Unfortunately, if you start to use Redis for volumes that I was just talking about, what you're going to learn is that the way that you scale Redis storage is by adding more machines when you need memory. And the machines that have a high memory are way more expensive than the machines that have a normal amount of memory, 7, 15, 30 gigabytes. And when you start to add machines, 32, 64 machines, to your infrastructure just to manage this type of workload, it starts to become expensive really, really quickly. You're not adding 64 machines in one location. You're adding 64 machines in 4 regions. And these 4 regions that you're adding machines on need to have constant uptime. And so you need people that are going to be, or processes that are going to keep your Redis up. And it's a bit tough. I can guarantee you it's great. And of course, sometimes the backup of Redis is going to add some extra latency every so often if you want to take proper backups. So it's a little bit heavy. We use, internally, we also use HBase. We still use HBase. It's a great technology, but the problem is that HBase made the decision to be consistent rather than available. And so it's very possible that if you're running a big HBase cluster, every once in a while, one of your region servers goes down for whoever knows what reason. And that entire region is going to, that entire interval of keys is going to stop accepting writes or going to stop accepting reads. And it actually happens fairly often if you haven't tuned your HBase cluster really, really well. And it took us, since when we started to use HBase, before we started to get a stable HBase platform, it took us about 2 years. 2 years of work and refinement on the backup process and on the speed and the performance and fine-tuning all of these instances. And it actually works great, but it's extremely expensive. And downtimes do happen, and downtimes are really, really expensive, and we can't afford them. So, of course, we tried Cassandra. Everybody does. Netflix uses Cassandra, so it must be great. And you know, 2 years ago, when we made this decision, Cassandra was at version 0.6.1, I think, or 0.6.0. There was a big difference between these two, even. It wasn't yet mature back then, but we constantly revisit all of our decisions. And the problem we had with Cassandra was really that it was very, very expensive to run, both operationally and in terms of hardware. And in order to show this, Netflix released last July, revisiting 1 million writes per second of an article that they wrote a few years ago, in 2012, I think. And in this article, they talk about building a Cassandra cluster in an automated way so that it's capable of handling about a million requests per second, which is about what Adderall's infrastructure is in need to handle. In the article, of course, they test 1 million writes per second. And they also talk about how the mix that they see inside Netflix is they write about 10% of the time and read 90% of the time. Well, At Adderall, the mix is about the same. It's about 10 to 90 or 30 to 70, depending on the time. And if you run the cost that Netflix comes up with during, and it's explained in the article, you're going to see that effectively the solution that we're using in DynamoDB is about half the cost. And all of this with 0 people involved in this. So half the cost, no people involved, and the system is the same type of requirement that we need in both cases. And we get it for really, really cheap and very little upfront cost compared to what Cassandra does. In this particular case, I would always recommend to use the 3 years reserved capacity inside DynamoDB. It's a bit cumbersome because you're buying 5,000 reserved units per increment, which gets a little complicated as you grow the database up over time. Your capacity is going to expire over time, scattered, and so you need to kind of keep track of all of these things. But the reality is that operational-wise and in terms of cost, 3 years reserved are going to pay off after 5 months. There's about, I think it's an 85+% discount on the price of DynamoDB to go in reserved capacity in an hourly way. You can see it goes from $130,000 to $15,000. Yeah, there's the upfront cost, and that adds another $15,000 on top, basically, over the 3 years. So all of this is really, really great. And of course, like everybody, this is not an open source technology. And so what is going to happen when maybe this is not adequate anymore? Or are we going to get locked in? Is this going to be a complicated deal to go through? How do we back up? Or we take out our data? Or what if they stop developing DynamoDB like everybody forgot about SimpleDB? So it's an interesting problem. It's, of course, what everybody asks about. The best way that I think you can look at this problem, and the way that we approached it is by looking at speed. There's been a lot of talk at the reInvent about increasing speed of execution from Andy Jassy's first keynote and Werner Vogel's second keynote, and multiple other talks from Amazon and non-Amazon people really highlighted the importance of speed. In today's market, if you are not Uber, you are the taxi companies. If you're not the hotel, sorry, if you're not Airbnb, you are the hotels. You're going to get disrupted if you're not going to move fast enough. And it's going to be a problem. So speed is a really important thing in today's world. And what does this all matter? Well, it matters if my team is not capable of executing, of running in a completely global environment, and I need to scale my database up to 1 million requests per second. And my team is not capable of doing this, not because they're not smart or because they wouldn't be able to, it's because they are too few. As a startup, you need to scale fast, and what we are focusing on is trying to operate on our product. And it's a bit complicated to focus on the product when you are spending all of this time in operating a database that needs to run at a scale that nobody has seen before, basically, or few companies have seen before. And there is another concept related to this about moving fast that comes from Martin Fowler, the sacrificial architecture. So what this means is that effectively we need to stop loving the software that we write so much, that we get so much weight in our head about retiring our software. It's really an impediment to moving fast if we get attached to it. And effectively, along the similar lines, Jeff Dean at Google said that what they do at Google is they design a system to scale 10 to 20 times what is the current load. And if it goes above that, they just throw away the system and start from scratch. This is a way to avoid making decisions that play well when you are a smaller company, and when you grow up, the solutions that you chose is inadequate. So going down to a little bit more, I think overall, this for us, being able to go fast and be able to get to a final product faster than the competition is far more important than being locked in. But on top of that, DynamoDB is not a special API. It doesn't have things that cannot be implemented by another database. And the only thing that we will be doing is operating a database. So rather than getting on us immediately the cost of operating a database like that, we'd rather move fast. And then afterwards, we can think about when we need it, if we need it, move a database like DynamoDB the moment that it breaks on our own ends and run maybe a Cassandra cluster or something. So all of this is fun and games, but it's more about business. So this is a 400 session, so I'm going to talk more about the technology. So if you talk about Cassandra and DynamoDB to the very kind and nice people at Netflix, among the many things that they will mention is that the main reason why they're not using a database like DynamoDB is that they still needed replication. Of course, Monday, I think, DynamoDB released the streams feature, and they also have an open source package to do cross-region replication now that it's all very handy. We did all of this stuff 2 years ago when none of these things were available. So it's complicated enough because of the scale that it actually is an interesting problem to tackle. So I'm going to talk about the way that the request handling architectures work for Adderall a little bit more in detail. So first of all, we use elastic load balancing. There's effectively two sides to Adderall. There is a data collection side, as I said, and there is a bidders side where we run all of our real-time bidding. This in particular is the bidders side, the ad serving side. So the data collection side is pretty much the same. So the elastic load balancing in front there is assigned to different exchanges, so that if any one of the exchanges had a spike in load or some kind of trouble that caused our capacity to be over-allocated to this exchange, because the elastic load balancing and the auto-scaling group are both too dedicated to a specific exchange, we can contain the failure to a single area. And we don't get to have latencies increases in different networks because, I don't know, Facebook or Google had a big spike in traffic due to some event that we cannot probably know. Then all of this data flows inside the instance. The instances here are inside, all of them are inside auto-scaling groups, and inside the auto-scaling group we run a supervisor that makes sure that all of these, that all of the processes that are important to the machine are properly alive. As I'm going to talk later about another daemon that runs on the machine that is not depicted here, that allows us to do to improve our availability profile. These instances are almost completely stateless. The black box the black box, which is our machine learning program, and the Erlang bidder are living in the same instance. They are communicating with each other, but they don't really modify the state of the machine, and they don't really have anything that they store in memory that is really, really important to be kept alive. So it's really easy for us to kill any one of these guys. And the way that we do the DynamoDB replication, all of these instances read from DynamoDB, is that we leverage Amazon Kinesis and Amazon S3. We're starting to play with Kinesis right now. Amazon S3 has been our rock-solid data transport platform, effectively, for the last 2 or 3 years. The advantage that we get, and also this helps with the lock-in problem very, very easily, really, is that when data flows inside Amazon Kinesis or S3, it flows through a very super secret replication magic box that I cannot reveal to you under even duress. And what this helps a lot, because this replication magic box is the only thing that writes to DynamoDB. Everything is piped through logs. And a very fine gentleman, the author of Kafka, wrote an incredibly nice article to read not too long ago about how the log is the best database. It's the best database because it has very nice properties. It's ordered. You can replay a log, and you can store it in long-term storage, effectively, for relatively cheap. And you don't really need to access it in a different way than sequentially. And so by having all of our data stored sequentially inside Kinesis or Amazon S3, at any point in time, if we decide to, we can go back 30 days and replay the last 30 days of data and store that in DynamoDB, as we're doing today, or maybe we can switch to Cassandra, or maybe we can switch to HBase, or God forbid, MongoDB. And so all of these different pieces have a very interesting inner working. So here's the basic logic of the replication magic box, which is you can't talk about if you exit this room. So it really is very, very stupid. I mean, we went to this and we thought there's a lot of different problems, but we took advantage because of this, of the fact that we have a single sorted log storage, basically. And we can replay this log. Everything is sorted. And no matter where it is, it's idempotent. We can basically run through this again and replay it and re-put it inside DynamoDB at any point in time, and the same data will be available in DynamoDB. And it's great. So we decided to go with the simplest property. And we just did the simplest thing. We have a queue. We fetch the first item from the queue. And we go from endpoint to endpoint in DynamoDB, and we update item. Now, this is great. It works. It's simple. There's a couple of issues. Yeah, it's not multi-threaded, or it doesn't write in parallel to all the DynamoDB clients, which is to all the DynamoDB servers. But the real big problem, and even if you use multi-threading, you're not going to solve this issue, or not solve it enough, is that this approach has a fairly low throughput for every one of the boxes, because you just do one operation per item, and you're receiving billions of items in your write stream of DynamoDB. So this, though, unfortunately, had quite a little bit of a pickle for us. We were using update item, and the thing that you think the most, the first thing that you might think about is trying to update multiple items at once. There is no batch update. And our key storage, our key structure was designed so that it was working fine for updating one item at a time. And so we needed to do a big switch. So this basically required us to redo the entire database. This was one of the cases where we had the data from the last 30 days or so in the logs, and we just went back the last 30 days and replayed the last 30 days and re-uploaded all of this stuff inside DynamoDB. We changed the key from the format that we have at the top, where basically we have a list of segments inside DynamoDB. Segment supports advanced types. So naturally, we want to use sets, and it's a very nice property, similar to what Redis does. And unfortunately, what we discovered is that not only it's really hard to batch update that system, it's also harder to have multiple different Storm clients that are updating the same key from multiple tables. And so we decided to make a move to a new key format, a much simpler one, and take advantage of the fact that you can query using the query operation inside DynamoDB. You can query using the hash key, and DynamoDB will return all of the segments that are attached to this key. You pay in a very efficient way also, because DynamoDB is going to pack all of the space used by these small key value pairs, and it's going to compress them in the smallest format possible, and you pay as if this was a single get operation, effectively, for the size of the compounded payload, effectively. So we played around with a few of these schemas before, and this ended up being the most efficient version, because now DynamoDB does have a batch put item, and we were able to change our magic box replication to be effectively something like this. So we were going through a queue fetch, instead of one item, a batch size for the item. And in DynamoDB, the batch size is 25. And basically, with just this simple change, just changing the key structure and a couple of lines in our code, we were able to go from one operation per item to be able to, in one operation, upload 25 items to DynamoDB. That's without multi-threading. That's 25 times higher throughput. Instead of having, I don't know, 50 machines to run the replication, we have, what is it, 2? It should be simple, but it's 9 a.m. So yeah, that code is all really simple, and we don't really use Python for this side. This is practically the code as we run it in production. There's very little things that change here. There's at the top of this code where we fetch things from a queue, and then we build all of the operations inside DynamoDB, and then we prepare to write to the different endpoints, and then we write all of these batch packages in every one of the endpoints. And then I conveniently left out 200 plus lines of error code and retries and exponential backoff, all things that honestly Amazon should solve. The SDK client has much better knowledge of how to use DynamoDB. I don't feel like we should be wasting our time. But yeah, whatever, other topic. So yeah, how do we do deployment? So we moved all of our state inside DynamoDB. The machines don't really have any state, and they all write into this common log, and this common log is now capable of being replayed, and we can run all the types of operations we want. We can store one of the most amazing things that happens in advertising, actually, really hard problem to solve, is that when a customer comes to us, they give us, it's a bit of a digression, but they come to us and they ask us to spend $50 throughout the world. And we need to be capable of moving these $50 from the West Coast to Singapore as the sun is moving. And it's really hard to do with a forecasting tool. And we're using a combination of Kinesis and DynamoDB to move all of these budget operations around. And so the state of the machines, instead of changing directly, we change it by having messages sent through DynamoDB that then are replicated worldwide inside DynamoDB, and that the machines read back the state and complete their own operation, even on Bootstrap. So this allows us effectively to move around something like 600,000 objects throughout the world and have less than 1% discrepancy from what we could be able to do from reading logs directly. So it's a really, really powerful system. And I know it might seem like inefficient to use logs, but it's really, really cool. I'm going to need to move really quick because I see the time. So we deploy typically using blue-green deployments. We use Packer.io to build the AMIs. There's very few scripts, and they run flawlessly in 10 minutes. We use tags, version exchange, and application to manage costs and to be able to identify clusters. And we use a small Python script to automate our release process. We do everything from here, and actually, depending on the team can actually decide to even automate the entire thing, and no human needs to operate the deployment. With this is what we use to do phase deployment and rollouts. Now Amazon release code deploy, so this was also wasted effort. But it's cool. It's nice to write these lines of code. So running through the lesson. Also, there's nothing special about it. We just use the Amazon tools and the Amazon APIs to release different pieces. As I said, it's mostly about building an AMI that is self-contained and no state on the machine, and you just are capable of running up and down your instances, and then you need to figure out how the deployment works, which is in itself a complicated task. So DynamoDB, we run 1 million operations a second. It's really tough. If your key space is not uniform and uniformly accessed, you're going to get throttling. How did we solve this problem? It's complicated. We added the tiny read cache. It's about a cache that lasts about 10 seconds in front of the bidders, behind the bidders in front of DynamoDB. And this cache has been able to reduce our throttling significantly. So this is on the right side, our write throttling. On the left side, our read throttling. This is that 3,000 at peak is on 100 plus 1,000. So it's at most at 3%. And for most of the time, it's around 0 on the read side. That's the part that it's really, really complicated. On the right side, we can always retry things. That's a bit offline, but we still have a really, really low throttling. It's very important. Even a very, very simple cache that lasts 10 seconds because of the locality of the requests that we see on the web leads to really extremely good results, and there's not a lot of usage of memory on the machines because of this. Do not hug machines. They're not our friends. Any machine that is special is going to be a single point of failure. They should not have names. They should have tags. If a machine is about to fail, every machine is running a daemon, as I said earlier. This daemon checks all the different places where the machine could go wrong. The disk breaks down, so it writes a byte on the disk. The Nginx goes down, so it tries to do requests on Nginx and tries to verify the whole flow from Nginx to the bidders to then the state of the bidders. If anything is wrong for 5 consecutive periods, which is about 5 minutes, that instance is completely killed. The logs, of course, are saved and shipped to S3 so we can do forensics later, but we don't keep that instance around. We're not friends, and we just need to keep the infrastructure available at all times. On top of that, as I said, machines are stateless. State is a really big baggage, and it's really complicated to move around when you're managing state. You start to talk about Paxos, you start to talk about Raft, or how do you move things around between instances or whatnot. You start to do some jumps that don't make any sense. So better go stateless and move all of our state inside DynamoDB or whatever other types of storage that we don't need to manage in conjunction with the releases of the same machines. So try to split the functionality and the state of these boxes. TCP load balancers, balance connections, not request. And it's obvious, of course, but you don't think about it when you see graphs like this. And this is a graph that is a 6-digit damage to the revenue of Adroll in 24 hours. What has happened here? C3s have been released, and it was around March 6th, 2 weeks after they released them or something like that. We deployed them, and what happened is that these machines were so efficient that they were actually not timing out that often. And so the first 3 machines that joined the ELB group ended up capturing all of the connections and didn't leave any connections for the other ones. This is the CPU graph of those 3 machines. So we're using about 60, 70% of the CPU of the entire cluster. And what was happening is that those 3 machines were running out of budget, but all of the other machines were not. And so we were not spending all of the budget that is up there. And there's many machines there. And it took us 24 hours to find this problem. And it cost a lot of money. And how did we solve it? Well, we had a short-term solution. We reduced the number of machines. They started to time out more, and everything went back to normal. And then afterwards, we thought, that's dumb. So let's put instead a random chance of closing a connection over time for every one of these machines. And so they started to update themselves. This means, of course, that your metrics need to be everywhere and perfect. When you deploy a system like this, distributed, there are really secondary, tertiary effects. It's really hard to figure out how everything is working during a deployment. Even an automatic deployment is not always safe. You need to have metrics, at least 1 minute latency, no more than that, 1 minute interval. And less is much better. You need to have the ability to see period-on-period views of your metrics and be able to alert on that. CloudWatch doesn't support this, so we need to implement our own on that. And you need to be able to do metrics math, subtracting different metrics or doing rate of change or integral or compositions of different metrics, because distributed systems are complicated and there isn't one single metrics that you're going to look at. When something needs to be alerted on, there's usually 10, 15 metrics that you need to look at exactly to understand what exactly has been happening. And you can't save on this. This is really, really important for your uptime. It's like doing the Japanese bow exercise where they are like blinded and running on the back of the horse, facing backwards, and they somehow manage to nail it. I don't know how they do it. So the most and the last parting thought before I leave it to Siva is that cross-team capacity planning is actually really, really hard. You have multiple teams. Amazon says that every team should be independent. They shouldn't necessarily communicate too much between each other because the cost of coordination is really high when the teams start to scale. And so you would like to be able to tell a team, write to this table, and to another team, write to this table. And then a third team that you didn't foresee comes up and decides that they need to write 50 billion rows in the same table as the other two. And suddenly, the other two systems start to fail. And so it's really complicated to manage this type of capacity. And DynamoDB is not there yet. I know the team is working on improving this aspect, but for now, there isn't really an amazing way to work around this problem besides writing throttling clients for your DynamoDB cluster. So trying to figure out how fast you're writing so you can ratchet down and set some kind of threshold in there. But other than that, this is probably the #1 thing that is hurting us because it's really hard to have coordination across teams if you want to move really, really fast. And thank you for your attention.
Especially the processing stages are decoupled from the storage. The storage decouples various processing stages. The other piece in the architecture is that there is a batch layer and a speed layer. For example, the data collection layer is a batch layer. For example, all the pixels or the JavaScript code that runs in browsers that plants the cookie and sends the data over to ad role is in the batch layer. That hits the batch layer, and then eventually gets globally distributed to the bid serving system, which is the speed layer. So getting into the specifics of that, in terms of the data collection and storage, the architecture is really simply an elastic load balancer that is sending all the requests out to EC2 instances in multiple AZs. And those instances are writing to Amazon S3 and also Amazon Kinesis, which is your storage tier there. decouple the other data serving layer from this. And in terms of the global distribution, now what happens is that Magic Box that Valentino talked about is actually the Apache Storm cluster here that is taking the data and actually distributing it to the DynamoDB database in the same region as well as in other regions. I've used US West region and the EU West region here. And there's other regions that gets distributed as well, for example, Singapore and potentially Japan. And so, putting it together, the data collection layer and bidding layer are decoupled from each other. And then the Apache Storm actually moves the data that is collected by the data collection layer to actually the bidding layer. And again, the stack is very similar in the bidding layer. There's an elastic load balancer. For example, the add exchanges communicate to the elastic load balancer and talk to the instances, behind the load balancer, and then the requests are served from DynamoDB there. So getting into one more level of depth, and really this is how their architecture looks like. If you looked at, I think this is, I'm not sure how much you can see from there. I tried to fit everything in a single slide so you can see the whole picture. What's really happening is here, this one is a single region, and this is US, let's say US East Coast, and then this one is the US West Coast. There are 3 stacks there. What they do is they take the single stack, the same stack is replicated in multiple regions, which is a slight difference. The US East region acts as the master. So in fact, all the data, if you look at the data collection tier here, the data collection tier is actually writing the data back to Amazon S3 and Amazon Kinesis in the US East region, which is their master region. And then the Storm cluster takes the data and distributes the data to DynamoDB in multiple regions, right? And that is the Magic Box there that's actually doing the distribution there. And then now the speed layer here, every ad network, they stand up a stack for every ad network. This is the high-speed layer that's actually serving requests at less than 100 milliseconds, serving 1 billion requests there. Million requests there. It's 9 a.m. on Friday, so trying to get my head together. So in terms of each layer here, in the data collection layer simply is built on top of Amazon EC2, elastic load balancing, and auto-scaling. The storage tier here is built, again, on top of S3 and Amazon Kinesis. As we talked about, the global distribution piece that is here runs on top of EC2. And similarly, the stack is inverse on the other side. The bids are being served from a elastic load balancer that is hooked up to an auto-scaling group, which actually fires up the various EC2 instances. So the summary here is that when you're building scalable architectures like this, think of your architecture, build decoupled architectures. There should be a storage tier that separates the processing tiers, and then use the right store in each tier. In other words, I think you cannot, whatever you do here cannot break the bank. For example, there is no need to have a large speed. They can wait for 30 minutes to an hour for the bid, for the data collection piece to update their database here. There's no point. Therefore, they picked a great data store there, which is S3 or Kinesis. They have a few minutes to replicate the data. And then in the case of the serving tier, they picked a very hot data store, which is DynamoDB, that can serve requests at any number of requests at a constant latency, a low latency. So that in my mind is the essence of their secret here in serving such high request rate at such low latency. So the summary here is that you can build architectures using Amazon services that can serve billions of requests per day. Really, it doesn't really matter what scale of requests that you have. You can actually use these primitives to serve those requests. With that, thank you very much for your time. I hope that was helpful, and it was a pleasure to talk to you.